So today I'm going to introduce the speaker. So today we are happy to have Professor Scott Watson from the Syracuse University. Scott and I go a long way back. Well, not that long. So Scott got his PhD at Brown University with Robert Brandenberger. He's a cosmologist. He likes to study dark things. He likes to study universe. After Brown, he had a postdoc at the University of Toronto in Canada, after which he came to the University of Michigan, first as a postdoc and then as a junior fellow of Michigan Society of Fellows. And that's at that point I met him over there. I was trying to figure out who's this bright fellow. Was talking nice physics to everybody. And so after that, Scott became a professor of physics at Syracuse University, and he's actually spending a sabbatical here. So his office is on a 7th floor, 706, right? 707. That's
like,
right. So it's
like Vega.
Yeah, so it's old office. So if you don't have a chance to ask him question today, you always have tomorrow, the day after tomorrow, the day after tomorrow, all the way until December 1st. So I would like to introduce Scott to you, please. He'll talk about cosmology and new physics.
It's okay to turn the light off.
Absolutely. So do you prefer baryonic? Okay.
Thank you for the introduction, and thanks for the hospitality. Many of you have already talked to, and I've enjoyed being here so far. If you want to know more about this talk, will be posted eventually at my website if I figure out how it works. And I have to acknowledge the research I'm going to talk about in this talk was sponsored by the Department of Energy, the National Science Foundation, and NASA. So here's your beautiful campus. We're located here. And in this talk, I hope to tell you a little bit more about how that falls into perspective. So I was told to give a very general talk. In November, I'll give a seminar, which will give you a headache if you want to show up for it. But here I wanted to give you an overview of my research topics, which have been called ADHD. And you're welcome to stop by and we can figure out something to work on together. So let me start with some of my students. So Jada is an undergraduate that I did some of this research with. Drew is also an undergraduate at Syracuse. Arnab will be visiting on October 30th and giving a seminar. He's my graduate student. And Kishan also was my graduate student that worked on part of the research we'll talk about today. So I wanted to speak to the younger people in the audience to begin. You're probably too young to know who this is, but I want to be your motivational speaker for a moment. But I did live in a van down by the river at some point. So anyway, the path of how you get to physics can be quite complicated. Please hold laughter. So I went to the University of North Carolina at Wilmington as an undergraduate. The reason I did that was Michael Jordan. I wanted to be a professional basketball player. Don't laugh. Basketball, it turns out, it's not for everybody, so instead I decided to get a physics degree. Luck always plays a role, but I feel like if you really are dedicated and want to understand something, and in particular for me, a main motivator, and I keep putting my picture here. I know I don't look anything like this now, but I like that picture. If you read Stephen's book, and I got to know Stephen well, Stephen married me to my ex-wife. Here's a picture of us. But the question was, why does the universe exist? Why is there something rather than nothing? And I can't answer that, obviously. But what I want to try to address in the colloquium today is, if we understood, and this is Stephen's words, how it works, then perhaps we could ask the question why it works. And I kind of miss my friend Joe Polchinski, who always thought I was full of shit, so that's some of the motivation for today. So to keep going, as has been advertised, there's much left to understand, but I want to convince you today, if you take anything away from this colloquium, that it's an exciting time to be doing cosmology. But if you don't have to take my word for it, so everybody knows, I guess, by now that we just got the Nobel Prize in Physics for artificial intelligence. So why not ask ChatGPT why you should be excited about studying cosmology? And this is kind of a summary slide of what I hope to convince you of. So we have new observational tools. Again, I did not make this slide. So the James Webb Space Telescope is very exciting. We're seeing things we never saw before. We now have a new medium, gravitational waves. We have CMB studies, which I will try to say a little bit more about, but that's another way we could measure gravitational waves. 95% of the universe is still a mystery. I was quite impressed, by the way, with this generation. It made the slide easy. And we have ongoing experiments that I want to hope motivate that you should care about, including CMB-S4. The theory bit, we try. So you have the multiverse, which I don't believe in, and we have inflation, which I do believe in, modified gravity and quantum gravity, so we're still trying to work that out. But the key point is that these connect with these observations, and it's interesting. And in particular, the James Webb experiment could help address this thing that people call the Hubble tension, which is the idea that the expansion rate, or the rate the universe expands at, I'm going to use the word redshift, but a bit ago, doesn't seem to agree with the predictions of inflation. But it's data-driven cosmology, and that's really the point I want to get at. And again, I will post slides on my website if you want to check that out. Okay, so let me show the early days of cosmology briefly. So this was an early model of cosmology, that everything was stacked on turtles. Then there was the various religious beliefs, and basically whether a theory was true or not was how well somebody could argue about it. So what I would like to convince you of is that picture has slightly changed. And in particular, cosmology is now data-driven. All right, so this is the summary of my talk, and I'll be done in a minute. Everybody can go and drink more coffee. So the current picture of the universe is something happened here. Some of us are trying to create ideas for that, but we're still working on it. But we do think that there was a period of inflation, and I'll try to convince you of why we believe that. Then, as the main point is, as the universe expanded, it cooled, and as things cool, they clump, and that gravity is attractive, and so it forms structures. So in this regime that we have here in the very early universe, we're talking about particle physics. So we're forming atoms, nuclei, things like that. But then around 380,000 years after this event, matter lowered its temperature to a point where light could escape. It no longer interacted with it on average. And what's kind of interesting about that is it's roughly the temperature of the sun. Then as that light escaped, it goes forwards in time. But gravity continued to compress these particles, that early matter, and it formed galaxies, clusters of galaxies, and then we get pictures today. So this plot has a lot of information in it, which I hope to explain in some detail. But the idea is that you basically have a baby picture of the universe around here, early in its life, and then you have the picture today, and you can ask what led from this time, very early, to the late time that we can see on the sky tonight. By the way, you can see this on the sky tonight as well. If you look at the cosmic microwave background, if you hold up your thumb, it's about the size of the moon. That is the size of the universe at the time that this light escaped from the cosmic microwave background. Also, I've already seen several good colloquia here, so I hope to do the same. Please interrupt me, ask questions if you have any questions, especially the younglings. All right, so thanks for coming. That's the history of the universe. Are there any questions? Okay, so let me just reiterate what I just said. So the point is, we have this baby picture. The light escaped from the matter distribution, whatever matter was, and that's the tricky point, which I'll try to explain in more detail. But we have matter here. The light stopped interacting, and then the universe evolved, and we can make a comparison. And one of the important basic physics principles of this is that because gravity is attractive and not negative, you produce these potential wells, and this is a figure by Wayne Hu. The idea is that when you have this gravitational attraction, this part will heat up, this part will cool off during these acoustic oscillations. And so that gives you these in fine detail now. When I was a grad student, this picture looked terrible. Now it's crazy important. And these little red spots correspond to the heating up in the potential well. And then these blue spots correspond to regions that weren't as dense. And you can really use this to quantitatively, which I won't do in this talk, establish what the matter distribution was in the early universe. And for people that care, Stephen Hawking's initials are right here if you have a keen eye.
Maybe you should tell us a little bit about how you measure temperature.
Well, that's complicated. And I'm not an experimentalist, but I mean, the original thing was the horn experiment, which they thought was pigeons, and then they shot the pigeons. But yeah, so this is about 2.5 Kelvin in the experiment. And today we have Planck in 2018 that measured this to great precision, which was, of course, a satellite. Now, if you want me to explain the details of the experiment, I'm sorry.
You measure the temperature because you measure respectively. It's Planckian. Almost completely Planckian. So this is from the distribution. You measure T. That's all.
No,
Depends on the angle.
Thank you.
I just say horn, the horn. Bell Labs. All right, so the main thing I wanted to emphasize is the early picture and then the late time thing with the experiments that we have today. So the difference is in the temperature teaches us about the contents back then. Now things got more sophisticated. We have a huge number of experiments. And again, I'm trying to give a colloquium, not a seminar. I'll give a seminar in November. But we have from the gamma ray spectrum with things like Fermi and Swift and Chandra, down to the radio level. We heard a very nice colloquium last week about radio signals. We had the Hubble Space Telescope. This is a bit out of date, so I don't have James Webb on here. But then we have ground-based experiments, and well, actually, Green Bank's right there. And then we have CMBS-4 that's proposed, and that experiment, which I'm a member of, is sponsored by the Department of Energy, the National Science Foundation, and NASA. So the idea is we can do the whole electromagnetic spectrum using a variety of existing, near-term, and future experiments. So we can make this quantitative. We don't have turtles going all the way down. Although maybe we do, I don't know.
Loss of gravity waves. Loss of gravity waves, because these are all electromagnetic.
Yeah, no, that's a good point.
But he said
I'll say more about that in a minute.
It's electromagnetic spectrum.
I'm saying space-time variations. That's not electromagnetic.
No, exactly. No, I'll say more in a second. Ask me, say something again if I don't.
Thank you, Scott.
Yeah. So just, I said to keep it simple. This is kind of simple, especially for the experts in the room. But the idea is from this data that we took with the temperature, we can find out huge amounts of information. So you can think of this as the change in the temperature of that cosmic microwave background radiation, which again started at the temperature of the sun, but after the universe expanded and it cooled, it ends up in the microwave region. So this is the change in the temperature, and this graph is very misleading, which I'll try to explain. And then this is the scale on the sky. So again, when this stuff, the light escaped or stopped interacting with matter, it was about 1 degree on the sky. So you can literally take your thumb and point it up there, and notice there is a big peak here. Now, the important point on this y-axis is a bit confusing because this is very fine detail. If I plotted this in a normal scale, what you would see is a flat line, and it basically says the temperature was the same everywhere. So if you had one universe here, and when we look out tonight, one universe was here, and one universe was here, and one universe was here. Why are they all at the same temperature? And that is what we believe is the proof that inflation, cosmological inflation, this rapid expansion actually took place. So that's what this green line is supposed to represent. Again, notice, again, I'm not an experimentalist, but notice these have error bars. So this is exactly what inflation predicts. There's a peak at the time of the universe. This part's a mess, and I have nothing to say about it. It's difficult. But this also tells you what the structure of matter was during this time. So for example, you might think the universe was made up of atoms. That would be the reasonable thing to think. You wouldn't get this answer. And these are called baryon acoustic oscillations. The other thing is the universe is isotropic, meaning that no matter where you look, it roughly looks the same. Again, what I meant by this is it's scale invariant, so it doesn't depend on the scale you're talking about. These are random fluctuations. Again, a motivator for the theory of inflation, because these fluctuations in inflation are generated by quantum mechanics. So they're quantum mechanical fluctuations that are blown up on large scales. And again, this is misleading because it's so sensitive. But if you took this down to less numbers, the universe looks the same everywhere you look. So this also proves the idea that the universe is homogeneous and isotropic, which is this FLRW model that we use in cosmology theory.
What is the y-axis?
It's the fluctuation in temperature.
What is the unit of its temperature square?
Microkelvin squared. Yeah.
Temperature square.
Yeah.
It's a correlation between temperatures at different
Yes.
spots on the sky, and it's in the Fourier transform. It's in the
Coefficient.
L's.
Yeah.
Yeah, it's a bit of a messy
It's
unit.
momentum space on this.
You make the assertion that it looks the same everywhere, but how much of the universe do you think you can actually see?
That's a very good question, and that's why I said this is a mess. So the visible universe lies within this, but then there's something called cosmic variance, and there's the visible universe. And here's the bad news, and this is what we sell to NASA to get our funding. The universe is accelerating, we believe. I'll comment on that in a minute, which means that we're seeing less and less of the universe, which is kind of depressing, if it doesn't change.
So you're acknowledging there's more of the universe than what our telescopes can
Yes.
see today or can ever see.
Yes, for now. No, it's, yeah,
It's beyond the horizon.
yeah.
So for example, you're only seeing 0.1% of what actually is out there, and your statistics are bad when you look beyond.
Well, yes and no. I mean,
Yes, go on.
I mean, to get into units, basically we see 5,000 megaparsecs. And that's done pretty good to predict a lot of stuff, which I'll put up in a second. On the other hand, if you ask me how big the universe is, I can't answer that. I got some crazy theories I can talk about with you later, but that's a bit ambitious. So I'm not saying I can answer that. All right, so after that light escape, the cosmic microwave background, that matter continues to clump, and this is a simulation from Chicago. Based on the data, this is what we believe happens. So those atoms become molecules, molecules become clumps, gravity keeps being attractive, and we start building galaxy clusters. And so there's this top-down building of what we see on the night sky tonight. So we're taking these initial conditions, the only point of this silly animation, that's the light coming, it doesn't interact with the matter, so we get the picture of what was there initially, and then we get the late picture of what we see tonight on a telescope. For example, we heard about Green Bank the other day. So you compare these two pictures and you try to piece together what happened in the early universe and what is going on now. And this is actually a simulation. This is a simulation from Chicago. This is theory, so that was just fun. But this is if you put something called dark matter in the early universe, this is the simulation you would get, and it agrees with the observations that we see tonight at the telescopes. If you put atoms, you do not get that answer. If you put crazy electromagnetic fields, you don't get that answer. If you put something I'm calling dark matter, please ask questions, then you get this answer. And so that leads me, well, let me just give you a review here. So we started out with some initial conditions, and we ended up with some galaxy clusters. Redshift today, in other words. And you would not get this picture from these initial conditions that are given to us by the cosmic microwave background unless you claim what I'm about to show you. So let me repeat that again, I guess. This is the observation. This was the SDSS collaboration. We have better data now, but I didn't have time to update it. I apologize. And this is theory. And if you compare these, and you smart experimentalists in the audience can, these agree to a high precision. So the theory seems to make sense, and it ain't atoms.
Excuse me.
Yep.
Qualitatively, I can see some visual similarities, but metrically, what would you compare? That this quantity in the observation is this, theory predicts that. Are there metrical quantities that you can compare?
I think you want this, maybe. I don't have the decimal places, but I don't know if this is getting at your question, but let me try. So the idea is when the CMB escaped, it's 26.8% dark matter, 4.9% atoms, and 68.3% dark energy. Today, I said that backwards, sorry. But at the time the CMB escaped, at 380,000 years, it was 12% atoms, 15% photons, 10% neutrinos, and 63% dark matter. And that's the comparison of the CMB measurements, which are incredible now, versus what we see today with things like SDSS. Is that what you're aiming for? Or?
We'll talk later.
Okay. So the part I'm trying to scare everybody about, or excite you about, because we need a lot of research done, what you think you know is 5% of the universe, according to these experiments, which there are many. And I can't talk about all the dark matter experiments today, but we heard many last week, and I'm sure we'll hear many more. So what's exciting about this, even though, I mean, first of all, LHC found the Higgs boson, and we should be excited about that. So if anybody writes a book and says physics has been done for 20 years, they should not write that book, even though I love the person I'm talking about. The point is that all of this, and even the baryons, even the atoms, require baryogenesis, which is physics beyond the standard model. All of this is physics beyond the standard model. Inflation, that I'm trying to motivate through that very precise graph, physics beyond the standard model. Why the universe is homogeneous and isotropic, physics beyond the standard model. And this 1 part in 100,000 density contrast we saw with at least the CMB, that requires physics beyond the standard model, and it points towards quantum gravity. So I'm trying to get you excited about this stuff. These are all problems. I'll be long gone, but you guys in the back of the room can solve all these problems.
But there are categories in the bottom that didn't propagate up. I don't believe in those the 10% neutrinos all disappeared, did they?
This?
Yeah.
Why?
Why what? Why do I believe they didn't disappear?
No, I'm just saying sorry. I'm saying that this would be better if it was the other way around. I'm saying the expansion is being taken, thank you for that question. The expansion is being taken over by dark energy. And if this keeps going, this thing will be completely dark energy.
But so 10% of the neutrinos should also appear in the upper picture or not? They're not 10%
No,
anymore.
they're negligible, yeah.
I see. They're squeezed out because they're.
Because of this beast that we don't understand.
So they're still there, but they're such a small fraction. They
Yes.
don't fit in the.
And I'll be a little more precise in a second, actually.
Good.
So I just want to say a little bit about dark energy. They do give Nobel Prizes for things that we are convinced could never be proven wrong, although you might have opinions about that. But one thing that's interesting is the result that dark energy exists. So this is the likelihood, if you're a Bayesian analysis. This is the amount of dark energy, and this is 0, and this is 0.7. So this is a 64 sigma result, which, as my colleague likes to brag, is the most precise measurement ever made. Anyway, it's fun. And it's also stronger than that now. But the main thing is that roughly 13.7 billion years after the stuff I'm talking about, we know the universe is accelerating today. That obviously is a challenge. There's talks of cosmological constants and such. All right, so I didn't want to put technical slides. I'm not going to. I just want to throw this out there. There are new ways to approach this problem. What is driving this acceleration? And I remember when I was a graduate student at Brown, and it might even be Rocky Cobb that gave the talk. But he said, thank God we don't have to understand condensed matter physics. Well, it turns out, if you take condensed matter physics and apply it to understanding this problem using methods of effective field theory, and if you don't know what I'm talking about, just ignore me for a minute. I'm not going to talk about this. But you can make universality classes, so we know the universe is accelerating. That's universal. But then what drives it is non-universal. And so you can put ideas like it's a cosmological constant in a multiverse or whatever words you want. You could modify gravity and say Einstein was wrong, stuff like that. But they come in classes, and you can take observations and put constraints on these coefficients, and that's stuff we've worked on for a while with people at Cornell. Anyway, that's not colloquium material, so no more about this today, unless somebody has a question. So the question is, what is the source of these fluctuations? I kind of already gave away the punchline. Well, we start with the CMB picture. We saw that it evolved, and then we get large-scale structure. So these are projections from CMBS4. But the idea is we believe in this idea of cosmic inflation. I was always told never try to explain this in a colloquium, but I am still defiant about it. So if you think about potential energy in your classical mechanics class, the idea is that during inflation, the energy is roughly constant. And if you turn to Einstein's equations and you ask what that means, Einstein's equations, the real, not the E equals gamma mc squared stuff, the real Einstein equations, it means that the universe would accelerate. So during this process, this ball's slowly rolling, and then inflation ends when the ball comes down and oscillates back and forth. And one thing I think is particularly interesting about this idea is I was talking for the aficionados in the audience about the cosmological constant. That's acceleration today. But acceleration in the early universe, by definition, cannot be a constant. And the fact that you have acceleration then and acceleration now, you might want to try to connect those two. That's challenging, and I can't do it. But somebody can in this room. So we have this process where it's not exactly constant energy, but it's slightly rolling. And every crazy theorist has written down an idea on how to solve this. So what's this plot about? So this is the amount of gravitational waves that would come from such a process. So these aren't like the gravitational waves that LIGO detected. These are early universe. And again, we heard this last week. But so this axis is gravitational waves. And this is how far you are from exact scale invariance, meaning that nothing depends on the scale, hence scale invariance. And these are all the crazy models that theorists have written down. And the main point of this slide is to show you that data is killing off all the crazy theory ideas. And the scariest part is one of the original ideas, which is called Starobinsky inflation, or R-squared inflation, which is not really theoretically motivated very well, seems to lie right in the sweet spot for the data, which is very frustrating. Or not. But the main point I wanted to get across with this is that we know a lot about what inflation is not, and that this data is getting so precise in the CMBS4 experiment, we actually will be down into this region. So it will rule out all the crazy theorist ideas. The other thing that is surprising, this is an old result now, but 2018, the Planck data showed these coefficients, again, this is a colloquium, so the amount that this inflation field interacts with other stuff, we know there's a standard model, I think, right? So the amount the inflaton, if I call it that, interacts with the standard model is very weak during the process of inflation and when these fluctuations are generated. And that's not just puzzling, it's a little bit confusing. And how bad am I on time? So this is the projection of what we're going to see in the future. This is CMBS4. So again, this is the gravitational wave spectrum. This number 0.003 sounds arbitrary, but it turns out that's very important for the various models. One model, which seems nice but seems difficult to realize, is the Higgs boson could be the thing that drove inflation, but there's technical problems I won't go into in this talk. And again, this is the idea of scale invariance. And so maybe I should just leave it at that, except if we actually did detect primordial gravitational waves through a seminar I'll give next month, we could actually determine the scale, or the energy scale that inflation took place at, and that might tell us something about the physics. Another issue, and this goes back to the question about neutrinos, if things are in thermal equilibrium at the time the CMB gets produced, We can put bounds on the number of effective radiative degrees of freedom. We call that ineffective versus the temperature. And you can even use spin, whether it's a spin, the new particle you want to propose. Let's say you want to right-hand neutrino. The spin 1, spin 1/2, spin 0. The CMB observations using this ineffective measurement could actually distinguish between the different spins. And at what temperature they were in equilibrium. Okay, so something that's kind of important to me that I've worked too much on. Again, we don't know what happens here. That's work in progress. But we have this period of inflation, which I hope I've convinced you is convincing. It's in your cosmology textbook, so somebody believes it. And then we have BBN and we have the CMB. But there's a space in between, and the irritating part about the space in between is that's exactly where weird stuff in the standard model is supposed to happen. For example, words you might have heard like supersymmetry or other ideas. But the idea is that we need to probe this region and figure out how inflation produced the standard model.
But light is not coming out of this, or electromagnetic radiation is not coming out of this region. I think you showed the 30.
Oh no, yeah, that's crucial actually, yeah, good point. So I mean the point is that radiation gets frozen out here and yeah.
Pardon, radiation gets frozen out at the end of inflation?
No, slightly after. So at 380,000 years.
Where was that on your picture?
This picture's more.
No. One just.
No, this one's more accurate, sorry. I mean here. So inflation ends, we don't know how long this lasts, but and you're asking a question that I think is important to emphasize for everybody. You might wonder, when I say this is 380,000 years, the current paper I just wrote says this could be infinite years. The point is we run the clock backwards, and I think that's an important point. So the way we understand this is we take today and run the clock backwards. That's why I'm saying 380,000 years.
Now what I'm asking about is, you showed the gap.
This space, yeah. I don't know.
And you said things, the photons got frozen out at the start of the gap. Is that what you meant to say?
No.
Good.
And I think it's a great question. So running the clock backwards, I know this is 380,000, but I don't know what happens here.
Yes. So you'd say that photons got frozen out at the end of the gap. Did I mishear what he said?
No,
Alright.
no.
Maybe you can discuss it after.
Pardon?
Maybe you can discuss it.
I think you fixed it.
Yes.
Yeah, I think you fixed it. I apologize. Yeah, I mean, sorry. Should have stuck with that. Yeah, so my main point is we don't understand this bit. Okay, so as we said, we believe that inflation took place. We have a lot of experimental evidence for that. So if you look at a standard cosmology textbook, as I mentioned before, I'm being repetitive, but we have slow roll inflation, it ends, and then the idea is that the inflaton, or this field that drives inflation, don't know what it is, but perhaps think Higgs particle. Back in the day when this was invented, we didn't believe scalar particles existed. Then there's that Higgs boson. But so it oscillates back and forth, and then the idea is it couples to other fields and would decay. Now, what's interesting about this is this process can be quite complicated. If there are any mathematicians in the room, it can be quite interesting. So the idea is that inflation had this slow roll era. We end inflation. Then we get these coherent oscillations. And then the idea is we're supposed to decay to the standard model and or any dark matter. and then we reheat, and that's actually when what we thought in the old days was the Big Bang, which is actually happening after inflation. All right, my animation's not working. There it goes. So, for those of you who have no idea what I'm talking about, you can think of the problem from classical mechanics where you have two coupled harmonic oscillators coupled by some spring. And the idea is that the inflaton is one of these particles, which is going down this potential. Inflation ends around here. This axis is energy, this axis is time. The particle goes down and it starts to oscillate. And depending on the coupling between the new particles to be born, let's say the standard model, or dark matter, we've argued that has to exist, you have to figure out this process. Why this is interesting is if you get into the details and you consider various couplings, you get things like parametric resonance or non-perturbative instabilities. If you have no idea what I'm talking about, this is the idea if you're pushing somebody on a swing and you push them at just the right time when they come back, you get, in this case, more particles produced. You would get them more elevated on the swing. You also get nonlinear dynamics and chaos, meaning sensitivity to initial conditions, turbulence, and then eventually, if all this stuff works out, you would thermalize to the standard model and or dark matter. These are simulations that we've done, but I'm not, again, this isn't a seminar.
Let me interrupt. This energy of that axis. What do you count into that energy? What's the energy of?
The potential of the field.
Is there only one field?
It depends on the model. But in my view, you can think of this as a clock field. It's spontaneously broken scale invariance, so that there's a potential that corresponds to this energy. I'm trying to tone this down for the colloquium, but I mean, this is V of phi versus phi, and your theory gives you the potential, if that makes any sense. But on the other hand, going back to the condensed matter comment, I mean, you can think of this as a phase transition, and this is some Goldstone boson that is corresponding to when this scale invariance is broken, if that makes any sense. Again, happy to talk. All right, so one of the challenges for this process is we're talking about this this coupling that obviously is really important, but the confusing point, and this is an active area of research, which I had the privilege of being at the Simons Institute Center where we tried to figure this out and figured out nothing. The data tells us, and it's important, data tells us, these interactions, whatever these parameters mean, these interactions, the spring constant, so to speak, is very weak. And these are well-known results from 2018 by Planck. So this picture of inflation seems convincing on one hand, and if, and most importantly, if we measure gravitational waves, that's a smoking gun of inflation. I think your future colloquium speaker will say that several times, Rocky. But the weakness of these interactions with other particles is very confusing. And it's actually a problem in effective field theory.
Why do you call it weak? The numbers are big.
I'm not making this very quantitative. I mean, I'm not telling you what these actually mean. This almost means no interaction locally. It depends on the 3-point function of the triangle that you're talking about.
Okay. We'll take
Come to the seminar or talk. Yeah, I can't really explain these really fast. I mean, my idea is, I mean this. But you're right. You're right. Yeah. The point is, if you write down models with interactions between the inflaton and some other particle
So
field,
something else has to be much bigger than this.
Yeah, I mean, these numbers aren't actually big. They look big, but
Okay.
I get what your point is. It's a good point. Okay, so I'm probably putting everybody to sleep, but let me just go back to your textbook for 1 second. So if you look up the theory of inflation, this is time. And usually what you know is there's something at the Planck scale that nobody understands, but they pretend to. And then you have inflation, which we really believe in. And then all of a sudden, the universe becomes thermalized. Everything's in thermal equilibrium. And then you go through and you produce all the standard model particles, you populate them thermally, and then everything's good and you get a BBN. So it turns out that if you try to realize such theories in UV complete theories, or theories that make sense at the quantum gravity level, this is possible, but it's not the only possibility, and one that actually seems to be just as likely is that you have inflation, and I can give you various reasons, but the inflaton itself, when it's doing those oscillations I showed you, they can lead to a matter-dominated era before Big Bang nucleosynthesis. We know by BBN there has to be thermal, but we don't know, this is that gap I was talking about. So if the inflaton just oscillates too much, that would give you matter domination. But then there are other reasons that you could believe, and I'll try to motivate that pretty quickly. So you have the picture in the textbook that it could be thermal, but you can also have the picture that it's non-thermal. And again, I don't know why I'm advertising Rocky's talk so much, but he probably will talk about this. I think I'll skip this. All right, just a couple equations, but then I'll stop. The main point of this slide, if you don't like this, close your eyes. The idea is that usually, if I'm talking about the Higgs mass, effective field theory is a strong thing. You focus on the energy relevant for the problem, and you don't need to worry about the Planck scale when you're calculating the Higgs mass, one might say. Or not. But in the case of inflation, that scale of energy that's necessary to get inflation to happen effectively is very close to the Planck scale. So just to do one equation real fast, if this is the inflaton, this is the kinetic term, that's its mass, this is its self-interaction. But there are higher order operators that would come into the problem, and this scale is near the Planck scale in most models of inflation. So you have to worry about, in jargon real fast, order 6 operators that would generate a scale of the whole scale as a mass for the inflaton, and this is what we call the eta problem. I am open to suggestions, and again, I'm on the 7th floor if you want to discuss. But in my opinion, the only theory of quantum gravity is string theory, and it's the only way that you can calculate these corrections in a self-consistent way. Okay, done with that. But that brings in a big mess, which I'm just showing in a picture. So if you actually build these models of inflation that are consistent theoretically in quantum field theory, but with these corrections, you get crazy pictures like this. So and it is ridiculous, but in some sense, the standard model is not the simplest thing you might have thought. But anyway, so you would have inflation somewhere over here in this higher dimensional space, and then instead you have this reheating sector. The coupling, that spring that's connecting the two particles, would be over here, and you have to deal with this mess. And it seems quite complicated to realize these couplings. So in summary for this slide, we really need to understand how inflation ends. Maybe there's a much simpler solution, but when we actually can calculate something and calculate the corrections and make sure the theory is not wrong, you get things that look like that. And when you get things like that, one thing that's to me interesting about string theory is that it predicts the existence of additional particles. So of course everybody here knows there's lots of particles in the standard model, but why shouldn't there be lots of particles in the dark sector, which we're talking dark energy, dark matter? What's that all about? So the consistency of inflation is requiring the existence of additional particles if you build it in the context of string theory, and that's this word I'm using called moduli. So the simplest example of this is right before Einstein passed away. He was trying to explain electromagnetism using an extra dimension, which led to Klein theory, and the radius of that extra dimension is the simplest example of what I'm calling moduli. All right, I think I had way too much stuff to talk about. I guess this slide's pretty important. So these non-thermal histories I'm trying to say that we should take seriously. Experimentally, forget the crazy string theory stuff, experimentally, Planck, many of the models, if you look at the data and get into the details, favor these non-thermal histories, meaning that it's not radiation dominated prior to BVN. We have not seen WIMPs or weakly interacting massive particles. This gives a way to still model build in the context of those. Thermal WIMPs are certainly in tension. This is an old plot, but I think yeah, this is difficult. But this new standard, non-standard history gives new phenomenology. On the theoretical side, I've tried to convince you that string theory models motivate. You get these particles and they oscillate. We saw the Higgs, we believe in inflation in the inflaton. Why isn't there more of them? And what would be the consequence? And then how do you transfer the energy to the standard model? Okay, so here's just a quick cartoon. This is what these crazy models look like when you get into details. So for example, you can have two membranes that are separated, and then as they're trying to come together, that drives inflation. They produce closed strings. Those closed strings become gravitons. So this is a mess, right? But people have looked at this. I just wanted to use this as an excuse to say hi to Lev Kaufman. Okay, so the last point I want to make, if you're like me, I can't pay attention for more than 45 minutes. Stepping away from crazy string theory, the idea that the hidden sector would just be one particle, or the dark matter sector would be one particle, seems a bit silly. First off, we have the strong CP problem, which some of you might know about, that introduces an axion. And then we have dark matter, which can't completely be the QCD axion. So you might think that maybe the dark sector is as complicated as the standard model. You could at least have two particles. So this is a little self-promotion, but the question is if it's, and this has been it's called the nightmare scenario, but what if the dark matter is only connected to the standard model by gravitational interactions? So that's something we've been trying to focus on. Fortunately, I put the word brain in there. Let's skip all that. So one possibility is something called co-decay, which first came out in this paper some time ago. But we're trying to understand how this would affect, this is jumping all over the place, I understand. But the goal with if it's gravitationally interacting with the standard model, we need to use cosmology to figure out what's going on. And in particular, the way that structure forms. I showed you those simulations of large-scale structure. And so this is one toy model. This has nothing to do with string theory here. It's a gauge theory. But the idea is that the dark sector decouples from the standard model. This is time. Actually, it's 1/temperatures of time. The dark sector decouples from the standard model while it's relativistic. This is a signature that astrophysicists can actually measure. So you have an A particle and a B particle. They remain in equilibrium. And then one particle could decay, and then the other particle freezes out. And again, I'm going really fast because I'm happy to talk about this stuff. But the point is the dark sector is not in thermal equilibrium with the standard model. If it would decouple completely. This is work in progress in some sense. We don't have a fundamental motivation for this, just some toy model we can write down. much like the standard model was at once. So the dark sector temperature scales differently than the standard model. That turns out something that you can test through observations of galaxies, because there's no Boltzmann suppression until the decay. I'm doing that thing where you're supposed to get technical in the last 5 minutes. So if this is the co-moving density of dark matter, and here at the x-axis is the mass divided by the temperature, this is your Cobb-Turner plot that you learned how dark matter freezes out. This would be what would happen if this dark sector had two particles, they're interacting, and then one decays and then one freezes out. And so you would get a different prediction for the amount of dark matter. You can write down a theory that is consistent. For example, if you pretend the dark sector is an SU2 gauge theory, you get something like this. Again, this is not a seminar. And then you could have this explicitly broken to a U1 symmetry through some dimension 6 operator, blah, blah, blah. But you would have some stable dark matter A sector, which is sort of like the W boson, and the decaying particle you could think of as the Z in an analogy. Do I think this is the right theory of dark matter? No. But I think people should think more about this and how we can connect it with observations. By the way, they're nearly degenerate based on the symmetries. Okay, I think I've said too much already. A lot of slides. Oh, jeez. Okay, in closing, can primordial black holes be dark matter? That's another idea that a lot of us have been looking at. And what was neat about that, and I think I should say this for the November seminar, but when first discovered, and I can explain why I don't buy this one either, but the LIGO observations found a number of black holes that were in a mass range that astrophysicists didn't predict. Now, again, to be honest, they were sensitive to this range, and astrophysics is difficult, as you all know. But it was still kind of cute to think maybe these could be all the dark matter. And in particular, the reason why is you don't need physics beyond the standard model except for the production process. So that's something fun to think about. And again, the point I was trying to do in this colloquium is tell you some of the things I'm interested on. We can all talk. Yeah. So again, observations. So this is the density of primordial black holes, and this is the mass of the primordial black holes. And the only point of this slide is you can put constraints on what it would be, so you can rule out these ideas as well. So again, precision, astrophysics, cosmology. So let me summarize. So what I hope I convinced you of a little bit is that cosmology is a way to get at new physics when the collider can't. Although, of course, the collider can, hopefully. So the most important thing is the CMBS4 thing, for me at least. If we detect these gravitational waves from inflation, it tells us the scale of inflation, so the scale of new physics. These observations will also put constraints on the presence of new light particles, so constraints on beyond the standard model physics. I gave you all kinds of crazy theory ideas about dark matter and what it could be. WIMPs are still in the game. If you make them half the dark matter and the other half's axions, they're still game. Or it could be primordial black holes, or it could be all three, which would really be a mess. But the point is, we can sort this out with observations. And the other, to me, exciting thing is this expansion history prior to BBN. Can we figure that out and get something done? And then, how does inflation give rise to the standard model in dark matter? That's a big order. But there's a lot of nice and interesting ideas floating around. And I'll stop there.
We have time for a couple of questions.
I have a question. Can you show the slides which at the end?
Which one?
Oh, okay. PMBH, yeah. This one.
Yeah, I was trying to skip over this because it's more of a seminar
Well,
level.
There's going to be a seminar.
Yeah.
But the idea is if you have early matter domination, you probably know Klopov.
Yeah, I know. Yeah.
So you can grow these black holes without putting signatures in the inflationary spectrum.
Popov.
Thanks. Other questions? Carl.
I heard you, I think, say something about properties of the dark matter. That if you put aside these, well, it could be this kind of a mass or that kind of a mass. Can you say that you have properties of dark matter that are more general than that are required by something?
Well, the main thing I think is a little bit new that
Like
we.
the interactions.
Yeah, no, good.
themselves.
Yeah. I mean, one of the things we're working on that's somewhat new, they have these things called microhalos. It's where it clumps in a certain way, and there are experiments like Galilei that would be able to detect the signals coming from this, and so you can put constraints on how it would collect and form these microhalos. So
Is there a way to communicate the fundamental aspect of that process? I mean,
well, yeah, I mean,
what are you saying about the dark matter?
I mean, so for me, the work I've done in this is if you have these early matter-dominated phases before BBN, their growth is enhanced, and so they'd be more dense, and you can't predict that if you just had regular radiation domination. Of course, it becomes model dependent. But these microhalos would form more commonly, and it's a way to rule out such models. And I don't know if I gave a coherent picture, but the idea is that connects in with the fact inflation predicts these other particles that make it matter dominant.
I think you're addressing how dark matter came to be. But I'm asking about if you could measure dark matter in the room, what properties of it could you predict?
I can't do it in the room. The people I know would do it with satellites and.
No, I mean in a parsec or so, is it got viscosity?
Yeah, no.
or-
Yeah, sure. I mean, the density of these objects would be higher.
Well, I don't want higher or lower. I
All
want
right,
to
so
know.
why don't you guys
Yeah.
square it up
All right.
after
All right.
the presentation?
Also, one other thing.
Carl,
You know,
after the
anything
presentation.
about the baryonic symmetry of the universe? Did you mention that?
Yeah, we need physics beyond the standard model.
Let's thank Scott again. Once again, so if you want to learn about those mysterious things, he's in 707. You should always have.